everybody! Welcome to day 2 of Echo Live, coming to you from the Michigan Science Center's Echo Distance Learning Studio. We're hoping you guys are excited as we are to do some more hands-on chemistry experiment right here from our studio. Now, if you joined us yesterday, we did some colorful chemistry in honor of St. Patrick's Day. Today, I thought that we might do some more chemistry and take a deeper dive into our states of matter using one of our very favorite science tools, liquid nitrogen. I can see we still have some friends joining in for our program today, so welcome. Tell us you're here in the chat. That's how we will be communicating during this program. I have lots of questions for you guys to answer from home, but I'd also love if you guys were to ask me questions, maybe make suggestions for things that we could try right here in studio. So go ahead, try out the chat feature for us. Let us know where you're watching from, maybe the name of your city, and if you have kids watching from home, tell us what grade you're in. Now today we'll be talking about liquid nitrogen. We keep it here at the Science Center in these devices that we call Dewars. If you're not familiar with a Dewar, most people haven't heard of that term before. But what I'm confident you've heard of is this piece of equipment that I have right here. This piece of equipment is a thermos. You might have a thermos at home that you use for taking your soup for lunch or perhaps keeping your coffee nice and hot for a very long time. The way these two devices work is actually based on the same technology. The Dewar was invented first in the late 1800s by a scientist named, you guessed it, Dewar. So Sir James Dewar actually invented this vacuum-sealed container in order for keeping liquids very, very cold for a long period of time. He actually created this by creating a double-walled container and then removing the air from inside the two walls. Since there's no movement of atoms and molecules in a vacuum, it allows the temperature to stay pretty constant. Now, a little bit later down the road, about 5 or 6 years later, the thermos company was invented. They used Dewar's technology to create this thermos, which is more familiar in our day-to-day lives. So this thermos is used for the same purpose, but more commonly used for people using these things at home. So lesson number 1, Dewar did not patent his idea, and so thermos actually makes a lot more money off of their devices. So always patent your ideas so that you can keep your name in science history. Now, our liquid nitrogen is here inside the Dewar, and we said that this stuff is extremely cold. So while I get on some safety equipment for working with our liquid nitrogen here today, go ahead and tell me in the chat feature, how cold do you think liquid nitrogen is? Take a moment to think about it. Tell me how cold is liquid nitrogen, and I'm going to put on my very protective cryogenic gloves, which are here to keep me safe from any liquid nitrogen that might get on my skin. And then I also have a pair of safety goggles to protect my eyes for anything that might splash up towards my face. Now I'm seeing some comments right here in the chat as they're rolling in. So we're guessing, how cold do you think liquid nitrogen is? So this stuff, if we're talking in terms of Fahrenheit, which is what we use here in Michigan, in terms of Fahrenheit, this stuff is about negative 321 degrees. If you're more familiar with the metric system, which is more commonly used in science, this stuff is about negative 196 degrees Celsius. Extremely cold stuff, so cold that if it were to get on my skin, it could give me instant frostbite. So we're being nice and safe and always working with our safety equipment when we're doing chemistry experiments here in the studio today. Now we'll begin by pouring just a little bit of our liquid nitrogen down here into the beaker that I have on the table. So if we pour it in, we'll start to notice a pretty interesting effect. We'll zoom down on this glass Pyrex beaker, which is made out of something called borosilicate glass, which means it can withstand this rapid change of temperature when it's coming in contact with this cold liquid nitrogen. Now you can see that this stuff is bubbling. You might even be able to hear just how rapidly this stuff is bubbling and boiling inside the flask. This stuff really is boiling right here at room temperature. Liquid nitrogen has to be negative 321 degrees Fahrenheit in order to exist as a liquid. If it gets any warmer, say 68 degrees like it is here inside our distance learning studio, it immediately begins to boil or turn back into a gas. Even though liquid nitrogen is something that we have to order and keep really cold inside these dewars, we experience nitrogen all the time. Even if you were to wave your arms around through the air, nitrogen is in the air all around us. We can actually feel it rushing against our hands if we move pretty quickly. Nitrogen makes up about 80% of the air in Earth's atmosphere. But if we want to be able to see liquid nitrogen, we have to condense it down into a gas. Condensation, or condense it down into a liquid. Condensation is a phase change, just like boiling. So all we're doing with our liquid nitrogen is changing its state of matter based on its temperature, which is all of the experiments we're going to do today. So first, let's have a review of our states of matter. There are 3 states of matter that we're most familiar with here on Earth. We have our solids, our liquids, and our gases. Solids are things like this table. They're rigid, they're pretty hard, they can't put your fingers through them, and they maintain their shape, at least here at room temperature. Now, if you were to warm up a solid, say something like an ice cube, we would have our first phase change. As we warm up the atoms and molecules in an ice cube, they begin to move around as they gain that energy from heat. Those molecules begin to flow, and they become our second state of matter, which is a liquid. Now, if you've ever taken liquid, say in something like a tea kettle, and placed it on the stove and gotten it really, really hot, we have another phase change. This liquid, as it gains energy from the heat of the stove, it will actually start to evaporate and turn into a gas. And those atoms and molecules will have even more energy, and they actually start to spread out even more. Gas molecules move extremely quickly, and they expand to fill whatever container they're kept in, and then if you open that container, they'll expand even further. Gas molecules have a lot of energy, but we can always reverse this process. If we think of, say, our water cycle, which we experience outside, we know that water in the air can actually be condensed into clouds using pressure or temperature. We also have precipitation, where those clouds turn back into droplet water and rain back down to Earth. And then in the wintertime, especially where we live here in Michigan, we can actually turn that liquid water back into a solid just by removing heat or by making something very, very cold. So we'll be doing an experiment on some of our states of matter that I have here in our studio using this extremely cold liquid nitrogen. To prove to you at home that this stuff really is boiling, right here inside this glass, we'll actually pour some right inside our tea kettle. Now, if you've used a tea kettle before, they make a pretty familiar sound. There's actually a song all about a tea kettle and what noise it might make. So think about that sound as we test out our first experiment. We'll take our liquid nitrogen and pour it down inside the tea kettle. We'll add just a little bit more since we've had some evaporation. And then we'll place our lid on our tea kettle and listen for that noise. We hear that tea kettle whistling, and so we know that that liquid inside is actually beginning to boil. Tea kettles make this noise because as our liquid turns into a gas, we said those molecules are starting to expand or to take up more space. Since they're taking up more space, they want to go somewhere, and there's only a small opening in the lid of this tea kettle for those gases to leak out from. If you think of how you might whistle with your mouth, right, you also create a small opening and push air through it. Let's try that one more time. You can even see that as I whip the container back and forth, we add even more energy to the system, which actually speeds up that evaporation process. Now you can see just how cold this tea kettle now is. You can even see some condensation, that accumulation of liquid water happening right on the outside of our tea kettle. Since this stuff is so cold and contacting the water vapor in the air all around us, that condensation is happening right here inside this room. Now, I have a couple more tests for us to try using our cold liquid nitrogen. I'd like for you to think about our states of matter and how we describe the movement of those atoms and molecules. What we've done is we've actually condensed the liquid in the air around us. We've condensed a liquid from the air around us by making it cold. But we said all of these processes are reversible. Now I'd like to do an experiment using a balloon. Now I'm going to blow up this balloon and tell me, as I blow up this balloon, what state of matter is contained inside the balloon? Is it a solid, a liquid, or a gas? All right, so we've got our balloon nice and inflated here, full of my breath, which you guessed it is a gas, at least here at room temperature. Now we'll take our balloon and drop it down inside the container. And what we'll do next is we are going to pour our cold liquid nitrogen all over the top of this balloon. Now think about what you think might happen to this balloon as we make the gas inside extremely cold. Think about the state of the balloon. Balloons are made of rubber, and so they're pretty stretchy, able to change their shape pretty easily as we manipulate the balloon. So think about what might happen. If you have a guess or a hypothesis about the results of our experiment, go ahead and type that in the chat. We'll zoom back in on our demonstration here on the table, and let's go ahead and pour our liquid nitrogen all over the top. All right, now we know this stuff is pretty cold, and so maybe it's so cold that we've actually caused somewhat of a crack or a leak in our balloon, because the balloon has certainly deflated. It's definitely out of our field of view, and it's really sunken down into the container or into the pool of liquid nitrogen at the bottom of this bowl. I think we should probably pull out the balloon and see what we can observe, at least from home or over the camera. All right, let's look around and see if we can find a hole in this balloon. I'm not seeing anything just yet, but that doesn't mean it's not there. But what you might notice is there's something pretty interesting starting to happen to this balloon. As we've removed it from the liquid nitrogen and allowed it to warm back up, our balloon has completely reinflated. It's completely gone back to its original shape, full of the gas or my breath. So let's think about what might be happening to those atoms and molecules. Everything is made of atoms and molecules, even the gases which are invisible that we can't see. Now, even though our breath is a gas at room temperature, just like our water that's condensing as it touches our tea kettle, my breath inside this balloon is actually condensing as well when it gets really, really cold. We said that all of these processes, these phase changes, are reversible. Since we can't create or destroy matter, we only change its form, we can actually do this again. So if I just put my balloon back down inside our pool of liquid nitrogen, we can actually reverse that process. As we cool down the molecules of my breath, they're condensing into a liquid. And just like we talked about with our states of matter that happen in the water cycle, these molecules are starting to take up less space. So much less space that we can almost completely deflate the balloon and be left with only my liquid breath inside, which is super disgusting. You guys definitely don't want to see it. But if we take the balloon back out and allow those molecules to warm back up, they regain their energy, and they're actually able to go back to their original distribution as a gas at room temperature, and our balloon will actually reinflate over and over and over again. Now, if you were a little disappointed that we didn't get to pop our balloon, I think I'm on your side. But we can pop a balloon using liquid nitrogen. So if we think about our states of matter, the reason that this demonstration worked is because we were adding the liquid nitrogen to the outside of this system, which condensed my liquid breath inside down into a liquid. But if we were to fill a balloon instead with liquid nitrogen, so the liquid nitrogen is now on the inside instead of the outside, we can actually cause the balloon to expand. We say that liquid nitrogen has an expansion ratio of about 700 to 1, meaning that in its liquid form, when it changes into a gas, it will take up 700 times more space. So that's a lot of space. If we want to fill a balloon, I've got another piece of equipment here. And this one is going to be a little bit loud. So before I do this demonstration, I'm going to put on one more piece of safety equipment, which is some hearing protection. If you're at home and you don't like loud noises, there will be quite a pop that you might be able to hear. Hopefully not too loud as it comes over the camera here. But if you're uncomfortable with loud noises, you might want to cover your ears as we go through this experiment. So my hearing protection is on. This time we'll be adding the liquid nitrogen into this test tube and then pouring it into another of our rubber balloons. So our liquid nitrogen is going down into our test tube. And we can see it rapidly starting to boil as it warms up to room temperature. I'll need to take off my gloves for just a moment just to stretch our balloon over the top, and we can actually see that balloon starting to expand. If we pour the liquid nitrogen into the balloon and trap that gas inside, here we go. We have a rapid expansion of gases taking place in a closed container, and our balloon will eventually lose its ability to retain its shape. All we're left with is a little sea urchin created by the explosion that took place inside the balloon. Now, I'd love to hold for questions for just a moment. I'll look for these questions to come in over the chat feature. So if you've not used the chat feature so far and you have a question that you might like to ask us here in the studio, go ahead and type those now. Now is a great time for us to again thank our sponsors. The Michigan Science Center has a boatload of generous sponsors that keep these programs going even while we're closed to the public and allowing us to bring programs to you guys at home. The DTE Energy Foundation is one of our largest funders, and they are loving bringing these programs to you guys at home. Now, I see some questions. I see that a lot of people think that this is really cool science, and you're absolutely correct. Let's see. I see some friends watching. See some friends watching from just up the road. I'm hoping you guys are loving this program. Let's see, I'll keep my eyes open for new comments. Will liquid nitrogen do that to any container? Well, let's see. Will it explode any container? Absolutely. So liquid nitrogen, like we said, has an expansion ratio that is amazingly large, 700 times its original volume from its liquid form. So if you were to put this in any closed container, you could have an explosion. So you never want to use liquid nitrogen at home to recreate this kind of demonstration. We are trained on these activities here at the Science Center. We are trained here and we're doing them safely. You definitely don't want to create an explosion that you can't control, but really all you need for an explosion is an expansion of gases in a closed container. So the answer is yes. What will you do next? That is a great question. Tomorrow on Echo Live, we're planning to talk about vacuum science. So if you think about the opposite of some of our explosions we're having today, we're going to be removing air instead from some systems and seeing what kind of experiments we might be able to try. Could you do this with different materials? That is a great question too. Liquid nitrogen can't be purchased by the average person. We buy it from an industrial supplier that usually supplies liquid nitrogen for welding. But if you'd like to try something similar at home with adult supervision, you can actually purchase dry ice from places like Meijer, or from certain grocery stores, which actually sell it for keeping your food cold if you're going on a camping trip. So if you'd like to try some demonstrations, check back on the Michigan Science Center's website. We'll be posting activities that you could try at home. Now might not be the time to go to the grocery store, but certainly something that you can try at home a little bit more safely. Does the balloon get hot or cold? The balloon got extremely cold. Now it's about back to room temperature just because the material is so able to adjust its temperature, but the balloon got extremely cold, which is part of the reason it popped, that as it became more and more rigid, it lost some of its ability to expand or to stretch, which also helped it to explode. Would a liquid spit-filled balloon feel like a very cold water balloon? My guess is yes, but that is something I would never want to experience and I wouldn't wish on my worst enemy. Great question, Nicole. How long have we been doing this show for? We've been doing this show here for years at the Michigan Science Center. I've personally been here for about 5 years, and liquid nitrogen demonstrations are some of my favorite. How does the balloon expand with the liquid nitrogen? Like we said, it's really just a container or a vessel for that rapidly expanding gas. But we did say that it got pretty rigid, and it did lose its ability to expand over time. How loud was the pop at the studio? Loud enough that I've learned to wear the hearing protection. I have forgotten in the past, and it does make your ears ring for a few seconds after. So not too loud that it's dangerous, but definitely loud enough that I will always remember to put on my hearing protection when I do that demonstration from now on. I hope it wasn't too loud from you at home. Sorry, Charlie, if it was your comment there. Ooh, would slime become super hard from liquid nitrogen? Yes. If you're able to make slime at home, which is one of those funky states of matter because it kind of falls somewhere in between a liquid and a solid, it's actually something that we call a non-Newtonian fluid. Whereas if you put it under pressure or you try to bounce your slime on the table, it behaves kind of like a solid. But if you were to leave your slime on the table for an extended period of time, it would actually start to flow and kind of spread out into a puddle, almost like a liquid. So slime is definitely able to be manipulated by forces of temperature and pressure. You can try that at home by just putting your slime in the freezer and see what kind of materials you might be able, or what kind of effects you might get. So we'll keep an eye on the rest of the in the comments section. We definitely hope that you guys are going to tune back in tomorrow for our next segment of Echo Live. If you enjoyed this episode, please share it on your Facebook page. We'd love to reach as many at-home scientists as we possibly can who are maybe at home looking for some activities that they might like to try. Keep an eye on our Facebook page for some of those at-home science experiments as well. So again, thank you for joining us for day 2 of Echo Live, and we hope to see you guys back here at 2:30 p.m. Eastern tomorrow. Bye, everybody.